Hello everyone. Uh, we'll start in a while. This is the 11th week of the Physics of Materials course. We'll start in a minute. Okay. Hello Karthik, am I audible?
Yes, sir.
Okay, let's start.
Okay.
So, the first question is, which of these materials is an intrinsic direct bandgap semiconductor? Silicon, germanium, gallium arsenide, zinc oxide. So,
Gallium arsenide.
uh, yes, you're right. So, first of all of them are intrinsic.
Yes. Intrinsic.
All are intrinsic because we haven't specified any doping. So, all of them are intrinsic. So, this is for silicon. So, how do we know it is direct or indirect band gap? So, we'll see the
Conduction band and the
yes.
yeah.
We see the conduction band. So, this is the conduction band, and this is the valence band in the bottom. This is the conduction band, this is the valence band. We'll see if the conduction band minimum and the valence band maximum. This is the conduction band. In this case, this is the conduction band minimum. This is the valence band maximum. If they are along the same uh, the reciprocal lattice space vector, at the same position in the reciprocal lattice space, or having the same crystal momentum. If it's like H cross K, then it is crystal momentum. If they have the same momentum. So we see that in the case of silicon, they are located at different locations. The valence band maximum and the conduction band minimum are at different locations. And
Yes.
so it's an indirect band gap semiconductor. So silicon is indirect. This is the case of germanium. So in the case of germanium, again we see that wherever, like at the position of the valence band maximum, there is also a local conduction band minimum, but the global conduction band minimum is somewhere else. And so again, it's an indirect band gap semiconductor because this is the global minimum, and this is the local minimum. So if we compare with the global minimum, then it's again an indirect band gap semiconductor. This is the case of gallium arsenide. In the case of gallium arsenide, if we see the global maximum of the valence band and the global minima of the conduction band are at the same uh, k vector, or at the same momentum. So this is a direct bandgap semiconductor, gallium arsenide. So one of the so a gallium arsenide is an example of direct bandgap semiconductor. And lastly, for zinc oxide, this is the case of zinc oxide, ZNO. So here again, if we see, this is the conduction valence band maximum, and this is the conduction band minima. So this is the same gamma point here and here, so it's the same point. Again, we see that they're at the same case position, the k vector. In the reciprocal space, they're in the same position. And so it's also a direct bandgap semiconductor. So both germanium and gallium arsenide and zinc oxide are examples of direct bandgap semiconductor. All are intrinsic, and silicon and germanium are indirect bandgap. So they have indirect bandgap. They're indirect bandgap semiconductors. This was the first question. I hope you understood this.
Yes, sir. Yeah.
So now we have the second question. So a material in which electronic transition occurs in two steps, what is it called? A direct bandgap material, an indirect bandgap material, a semiconductor, or a metal?
One is indirect band gap, two transitions. Semiconductor also comes in.
Yes. So it is an indirect bandgap, and it is also semiconductor, but only if it is indirect bandgap. So we will have a thorough. It's a factual question. We'll try to solve it. So we saw the example of silicon here, right? So in the case of silicon, it is known that this gap is 1.12 eV, and I also would have seen in literature that diagram of this of silicon. So this is the energy. This is the reciprocal space. So let the reference be 0 of the valence band maximum. This is the valence band. This is the conduction band. Conduction band. And for silicon, this is 1.12 eV. So what we say that okay, like there will be a photon that increases the energy, and then there is a phonon that increases the momentum. So you need both of this at the same for the transition to occur. But for that, the photon must have negligible momentum, and the phonon must have negligible energy exchange. So what I mean, I'll solve it and we'll see what I mean. So the two steps are basically photon adsorption or release, and phonon absorption, sorry. Or release. The system has to either absorb the energy of a photon and as well as absorb the momentum of a phonon. But both photon and phonon have energy and momentum. So the question is, why are we ignoring the momentum of photon and the energy of phonon? So we are ignoring these two values, right? We are ignoring the momentum of photon and we are ignoring the energy of a phonon. So this is allowed only when, so this is applicable only when the energy of photon is much larger than the energy of phonon, and the momentum. So in the case of the systems, these are called, in crystalline systems, these momentums are called crystal momentum. It's not the momentum that we have in the case of like mass into velocity in the case of classical particles. This is different from that. It's called crystal momentum, but it has the units the same as the momentum of classical particles. The momentum of photon must be much smaller than the momentum of phonon. So this is understood, right? Why am I saying this?
Yes, sir.
Because we are ignoring, right? When we are saying that, okay, this is a vertical transition like this, we are ignoring the change in momentum. And when we are saying horizontal transitions like this, we are ignoring the change in energy. So now let's take the example of silicon, which has a band gap of 1.12 eV.
Sir,
So let's.
will this be anywhere connected to the optical applications?
This is for optical applications. Like if you want direct band gap for optical applications.
Yes.
But okay, we will go ahead with that. Like we'll talk about that later. Now I just want to talk about the energy and momentum. Why are we ignoring these things?
Okay.
Like we will be calculating, because you would have seen like arguments, but we'll actually calculate this. We'll show that the energy of photon is much larger than the energy of phonon, and the crystal momentum of photon is much smaller than the crystal momentum of a phonon.
Okay.
We'll just solve it.
Okay.
So first of all, let's solve for the contribution of a phonon to energy. First of all, we'll solve contribution of phonon to energy. So how do we find this value? So E is equal to hc by lambda. We know this. This is the Planck's constant.
And then speed of light and
But this is in the case of phonon.
phonon.
So this is actually not C. I should edit V, because C is dedicated for the light speed. V is the velocity of sound, because these are lattice aberrations. These are matter waves, and sound is a matter wave.
Okay.
Velocity of sound in silicon, because we are solving for silicon. And wavelength, because these are matter waves, so there are like atoms everywhere, like lattice, and so all of this will vibrate, right? This will vibrate, this will vibrate. So we can say that approximately the lattice parameter is the wavelength. This is an approximate, this is an assumption. It will be obviously a multiple of this or a fraction of this, multiple of this. So it's an assumption that is that almost equivalent to the lattice parameter. Unit by
Okay.
A, lattice parameter. So the exact value doesn't matter. We'll just compare the orders of magnitude difference. So now if we put all these values here, so it is 6.6 10 power minus 34 into the speed of sound in, okay, let this be approximate. I'm not exactly sure, but let it be around 6 into 10 power 3. This is the approximate speed of sound in meters per second. And it's a lattice parameter. So lattice parameter of silicon is around, I think, 5.4. 5.4 into 10 power minus 10 meters. It's 0.54 nanometer. And this is in kg meter per second. Oh, sorry, this is in joules. So we have to convert into EV. If you multiply it by 1.6 into 10 power minus 19, you will get it in EV. This is the energy supplied, energy of a phonon. Now, if you multiply all these values, what is the? It is 6.6 into 6 divided by 5.4 into 1.6. Okay, so it's approximately and minus 3, 4, 10, 19. It's approximately 0.05 EV. Right? 19 plus 10, 29.
0.4583. Okay.
It's around 0.05 EV.
Yeah.
And this is much smaller than 1.12 EV.
Band gap of
Which is supplied by the photon. Right. This is of the phonon. Sorry. So the phonon. This is of the photon. Right?
Yes.
So that's why the energy of the phonon is much smaller than the energy of photon. So that is why we show that the energy change because of, like, let's say photon is this much, but a phonon is negligible. It's almost no energy change. But we will now we will show that actually the photon momentum is also. I should draw for clarification. This is the valence band. This is the conduction band. This is E. This is K. Now we will show that indeed the change in momentum is very close to the y-axis. So the energy of electron is not like this due to photon. That is what we'll show now, and this is the correct one. So for that, the momentum of the photon should be much smaller than the momentum of the phonon. So we have contribution of photon to energy. I will study contribution of photon to momentum. So what is the formula for crystal momentum? It is H cross K. So it's nothing but H by 2 pi into 2 pi by lambda, which is basically H by lambda. So again, if you put the value of H, 6.626 in 10 power minus 34 divided by lambda was around 5.4 10 power minus 10. by minus 10. This is kg meter per second. And so it is approximately
1.23 into 10
uh,
minus 24.
yes, minus 24 kg meter per second. This is the contribution of phonon to momentum. And now we'll find out the contribution of photon to momentum. So for this, we need to find out the value of k, the wave vector. So we see that energy is equal to 1.12 eV, the band gap. Where is it? I think it is 1.12. It is 1.12 eV. That is the band gap. And E is equal to c by lambda. In the case here, c is the speed of light. So from this, we can find out the value of lambda. Now, this h and c, so it is, if you calculate this value and convert into EV, it turns out that hc is 1.24 EV into 10 power minus 6 EV meter. This is a value that is helpful if you remember. You don't also have to calculate it and then convert to EV. If you remember this, like calculate this value, this comes out. So now lambda is equal to then 1.24 10 power minus 6 by 1.12 meter. So if you want to find out now the momentum, it's equal to h cross by k into k, which is basically h by lambda 6.626 10 power minus 34 by 1.24 by 1.12 10 power minus 6. This is approximately 6 into 10 power minus 28 kg meter second. It's understood, right? What I did here.
Yes, sir.
So now if you see here, the momentum, if like let's say if we denote it by p, let this be p of photon, and this is the p of phonon. P is the momentum. The p of phonon is 10 power 4 times the p of 10 power 4 times, right? 10 power 4 times the p of photon. So the momentum of phonon is much larger than the momentum of photon. That is why we show in an image like this that the momentum change because of photon is negligible. So if again we draw it clearly, So if this is energy cross k, let's say crystal momentum, or simply wave vector k. So, and this is the valence band, conduction band minimum. Then the energy supplied by uh, the photon is very high, but the momentum is negligible. So it's very steep like this. Most of the energy is supplied by the photon, and very small amount of energy but a maximum amount of momentum is supplied by the phonon. And this is why it is a two-step process. One supplies the energy and another supplies the momentum. Is it clear?
Yes, sir.
Hmm. I hope I didn't make any mistake in the numbers. Okay. So in the case of direct band gap materials, you will need both of them at the same time, which is why the probability of electronic transitions is low, because it took us two steps in the case of indirect band gap materials. So this is the third question. Both allowed electron energy versus wave vector and allowed electron energy versus pressure diagram gives the information about the band gap in a material. So in the last class we studied about this Brillouin zones and uh, how do we have, how do we can understand the concept of band diagrams from this Brillouin zone diagrams, E versus K diagrams. So what we studied is this. I will again draw the what it looks like. So we have the wave vector or h cross k crystal momentum, whatever you're comfortable with, and so we have energy in y-axis. And we had discussed that there are Bragg planes, which are perpendicular bisectors of reciprocal lattice vectors. At okay, let this be the separation of pi by a, where pi is the lattice parameter in that direction. Let this be in one dimension. So we showed that. So these are Bragg planes where diffraction of electron waves takes place, and so it would look like something like this. It should be symmetric because it's the same. Yes. So we said so these are the allowed energy levels or its Actually, there are bands. They're the allowed energy bands, and these are the forbidden. Okay, so now if let's say the electron is occupied till here, and this is all empty. Let's say this is empty. Now the electrons are occupied till here. Then this is the band gap. This is the valence band. This is the conduction band. If electrons are occupied to the shaded region. And so this is how, from the electron energy versus wave vector diagram, we can find out the band gap. And you would have also, you can also go through a more thorough derivation about this. It's called the chronic penny model. So the chronic penny model, you can actually see find out that how does the width of the bands and the distance between the bands varies in a material. This is thorough calculation for that. So using the energy versus wave vector, you can find out the band gap. This is the first thing. And second, we discuss about electron energy versus pressure diagram. So there is something called the tight binding model or approximation. So in the tight binding approximation, we talk about the how if we are applying pressure and bring the particles together, then even then you can study about the band gap. So why it is called tight binding? Because in this, the assumption is that even though all the atoms are free initially, the electrons are tightly bonded to each atom. Electrons are tightly each atom. That's why it's called tight binding approximation. So what we do here is that let's say we have two atoms which have shells so in this the outer shells are very close to each other, but the inner shells are very far from each other. This is the outer shells. The electrons here are very close to each other, but the electrons here are very far from each other. So what happens when you bring them further close? You apply pressure. What happens when you apply pressure and bring them closer? What will happen? what will happen is, so now what happens, because these two atoms are identical, both this atom and this atom, let's say they have the same quantum numbers, so they have basically the same quantum state. And if these two are coming together, they cannot be at the same quantum state anymore. The quantum numbers have to change, because there is this Pauli's exclusion principle. Okay, let's just say, so initially the energy level of this atom, of both the atoms, is something like this. This is the ground state, let's say, and then let's say this is the initial energy levels, n equal to 1, n equal to 2, n equal to 3, equal to 4. Now when they come closer, when these two atoms come closer, when these two atoms in the outer shell come closer, then the Pauli's exclusion principle comes into effect, and the band splits into two discrete energy levels. So this energy level splits. But this happens only for the outermost atoms. Why? Because they are much closer to each other compared to the inertial atoms. So outer energy levels will split. And why it splits? Because of the Pauli's exclusion principle. And what does the Pauli's exclusion principle say? No two quantum can occupy the same quantum state at the same time. And therefore, since both of these electrons were at the same quantum states, they decided to split off to different energy levels. Now what happens? So okay, this is n equal to 2, so let's draw, this is a slight mistake in this diagram. There have to be further energy levels. Okay, it's okay. Anyway, for representation purposes, let this be n equal to 1, n equal to 4. So now what happens? The inertial electrons are farther from each other. So what you will get is, I'll draw the final result. So if this is the interatomic spacing, and this is the energy. So initially we had energy levels like this. We'll again redraw them here. So this is, so let's say there are 3 energy levels. So the outermost, this is the outermost, this is the innermost, the outermost, if there are, let's say 6 atoms, let there be 6 atoms. that are coming together, then each of the energy levels will split into 6 discrete energy levels to accommodate 6 atoms which were initially in this having the same quantum numbers. It will have something like this: 4, 5, 6, divided into distinct energy levels. But and then, since this is like little this energy level is located far from the outermost energy orbital energy level, they can come a little bit more closer. So again, it will break into 6 levels. While the innermost orbital level can come to the like the minimum spacing, interatomic spacing, and then it will again break into 6 levels. Now what happens? Let's say if you take this particular position, and let's say the electrons are occupied till here. Okay, actually we have said that this is the outermost, so let this be the outermost. So electrons are located or present only in the shaded region, and these are the energy levels which are not occupied. Unoccupied energy level. So in this particular position, there is a band gap here. This is the band gap. Now, if you apply pressure, what will happen? The atoms will come more close to each other, and thus the band gap will change. It will become smaller. So as pressure is increased, as pressure is increased, the band gap decreases. You can see here from this diagram, as the pressure is increased, increasing the pressure, the interatomic spacing decreases, and the band gap decreases. So if you draw it, it looks, if you now draw a pressure versus, see, since the pressure and the interatomic atomic spacing are related, you can draw an energy versus pressure diagram as well, and that will look something like this. As you're applying the pressure, the energy levels are getting split. These are the splitting energy levels. So these are the energy levels that are getting splitting. But the application of pressure, and the band gap decreases with an increase in pressure. You can do it like this. And so even from a energy versus pressure diagram, you can calculate the band gap. The band gaps are different in different locations, and here it is metallic in this regime. So both from the electron energy versus wave vector and electron energy versus pressure diagram, the band gap of a material can be found out. So the answer is true. Is it clear?
Yes, sir.
The Milan zone. Boundaries. Whichever you all are comfortable with, whichever terminology. So this is what something that we were talking about earlier. A material having what kind of band gap, direct or indirect, is desirable for for light or sound navigation application.
So D is one of the options.
Yes. First of all, like sound has nothing to do with band gap, so both of them won't be the answer. It's either direct or indirect. So the answer is
Direct.
direct, because as we had discussed earlier in the second question, that indirect requires both photon and phonon for energy, for momentum. Whereas in the case of direct, requires only photon, because conduction band minima and valence band maxima are located at the same wave vector. No momentum required. So this is an easier process. It's a single step process. Therefore, it is more effective. It's a more easier process. And therefore, for anything related to like incoming of electrons, so this what we have like this, right? Okay. So this is the so there's no change in momentum that is required. You only need a change in energy. So let's say there is a hole here. There's an electron here. Electron can come and occupy this hole without any change in wave vector, the crystal momentum. Crystal momentum or wave vector. And this releases energy in the form of light. So direct band gap is always desirable for applications related to light. So the next question is, in conducting material, electron scattering effects do not exist.
It exists.
It exists, so the answer is false. So in the initial classes, we had discussed that when electric field is applied to the nearly free electrons in a crystal, then the you can, so with the help of Newton's law, which is like F is equal to ma, we wrote that m dv by dt is equal to the electronic multiplied by the electric field. But we also added a dissipation factor, v is the velocity. So we added a resistive term. And why is the resistance? Because of scattering centers, scattering effects. Because of scattering effects, there's a resistance. And so, which is why we had drawn a diagram like this, that with time, velocity, it will saturate. We call this the drift velocity. The concept of drift velocity exists only because we have a resistive term inside the material, which is because of the scattering effects. So scattering effects are always there in any form of any crystal, whether it's like metallic crystal or a semiconducting crystal, it's always there. And should we go deep into this? Okay, let's talk about it. Uh, and there are different scattering effects. So what are some common scattering effects? So one of them is, let's say it's a doped semiconductor. Then there will be ionic impurities or the ionic dopants which have been ionized. For example, if it's a doped silicon, boron doped silicon, then you will have boron positive ions which will attract electrons towards it. So, and they will cause a Coulombic scattering. And if it's uh, like n-doped silicon, then you have negatively charged nitrogen ions which will deflect, which will repulse the electrons away. So, in they will have ionized dopants or impurities. So, what will they do? Coulombic interactions with electrons. So, as the dopant concentration increases, the scattering effects will also increase. So this is one kind of a doping. It's called ionic impurity scattering. Then there are other scattering effects also. So there can be this lattice phonon scattering, or phonon scattering, whichever. This is the interaction between phonons and electrons. There can be this electron scattering, which we had ignored. Electron scattering. There can be, because if you have if let's say if we have something called a MOSFET, we have metal oxide semiconductor, and then in the semiconductor the electrons are flowing very close to the surface, and if the surface is rough, then there will be again scattering of the electrons. So if we have surface roughness scattering, so all of this will scatter the electrons. Now if you talk about the drift velocity, this drift velocity, so we can write drift velocity as mu into E. It's called the mobility. And the total mobility total mobility depends upon the effect of all of this. It has the effect of all kinds of scatters. And so the final drift velocity is actually being affected by all of these kinds of scattering effects. Therefore, all of these materials have scattering effects. They undergo, all crystals undergo scattering effects, including semiconductors. So the answer is false. It's 358. Okay, let's see how much we can complete. The electronic conductivity of a metal depends on how many numbers of, like, what kind of electrons in the system.
Free electrons, and then total number of electrons.
Okay, so we'll solve it. We'll solve it. So first of all, like, what is the dependence of the electronic conductivity on the, like, if this say, like, let's say n is the number of electrons, we'll define what these kinds of electrons are. So is, like, with what is the dependence on, let's say, what is the kind of dependence? What is I? Is it like one or some? What is the value? So we'll solve for that. Is it a linear dependence? Is it an exponential dependence? Logarithmic dependence? So let's find it out. So first of all, we start from the Ohm's law. What is the Ohm's law? The current density is proportional to the electric field, and there's a constant of proportionality which is called the electronic conductivity. The current density applied electric field, this is electronic conductivity. Then we can also find out another expression for current density. Let's say we have a wire. Let's say we have a wire, and the wire has a length of L. Let the current, let the number of, like, let N be the electron density. And let's say it takes time t for electron to move from here to here. That is the time taken. And so you can find out another expression for the current density, which is basically the total number of electrons, which is if this area is A, if this area is A, total number of electrons, which is N into A into L, flowing per unit area, per unit time, and multiplied by the electronic charge. So this A and A will get cut. So N E L by T. Now we know from the previous question that there's a drift velocity at which things will move. So this is nothing but the drift velocity. This is N E V D. Drift velocity. So sigma. So we can again put these two equations together, and we find out that sigma E is equal to NEVD, or sigma is equal to NEVD by E. So sigma is actually proportional to the number of electrons. That is the first thing. So it depends on the number of electrons. Now, what kind of electrons are this? Again, we had just a few classes ago that if you draw a potential versus position, This is potential versus position diagram of electrons in a system. It will look something like this. There are ionic cores here. And the electron levels are like this. And only these are bounded electrons, and these are nearly free electrons. So only these electrons can move throughout the material, right? Because all of these bonded electrons are bounded to the ionic cores. So, so conductivity is dependent only on the number of electrons which are nearly free for the free electrons. Therefore, the electronic conductivity is depends on the number of free electrons which are actually nearly free, and the free electrons are consisting of valence electrons. So option B and C are the correct answers. Okay. Okay, I think we can stop here. We'll discuss the other class in the class. It's already 4 p.m. Okay, there's no point in hurrying. Okay, we can stop here. I guess it's already 4 p.m. now.
Sir, that doubts I had from 7th week and 10th week.
In the assignment.
Yes.
Okay, can we discuss it next time?
Ah, next week.
Okay, okay. We'll discuss it next time. That will be the last class, or you can. Okay, we'll discuss it next time.
Okay.
Okay, after the class maybe.
Yeah. Okay.
Okay, chalo. Okay, we will stop here, and
Okay.
I hope you got some insight.
Yes, sir.
Okay.
Lots of information. Yeah.
Okay. Thank you for coming.
Thank you.
Bye bye. Take care.